an unexpected visitor from another star system barreling unannounced through our inner solar system inevitably sparks intense curiosity, fascination, and no shortage of speculation. The cosmos has long held the imagination of humanity, from early stargazers charting the movements of planets to modern astronomers probing the far reaches of our galaxy with powerful telescopes and sophisticated instruments. When an object from beyond our solar system enters our cosmic neighborhood, it is impossible not to wonder about its origins, its composition, and its purpose. Such an event captures the attention of both the scientific community and the general public alike, inspiring debates, theories, and a flurry of observational campaigns aimed at uncovering the truth behind the interstellar visitor. The third such interstellar object ever discovered, 3I/Atlas, is no exception. First detected in July 2025, this enigmatic object immediately drew comparisons with the previous interstellar travelers, Oumuamua in 2017 and Borisov in 2019. Each of these prior visitors had introduced its own mysteries and debates, challenging astronomers to rethink their assumptions about what kinds of objects might wander between stars. In the case of 3I/Atlas, initial excitement was amplified by the speed of its approach and its unusual trajectory, which indicated a hyperbolic orbit, a clear sign that it was not gravitationally bound to the Sun and originated from somewhere far beyond our solar system. The mere fact that 3I/Atlas had managed to enter the inner solar system, a region dominated by the Sun's gravity and populated with planets, asteroids, and comets, made it an extraordinary opportunity for astronomers to study interstellar matter up close. Despite early speculations, including some claims that 3I/Atlas could be an alien spacecraft or a probe sent by an advanced extraterrestrial civilization, growing evidence strongly supports a natural origin. Observations conducted with a variety of telescopes and instruments have revealed characteristics consistent with a true comet rather than an artificial object. Most notably, scientists involved with the NOIR Lab Educational Observing Program, utilizing facilities such as Gemini South in Chile, have been able to capture detailed images of 3I/Atlas that show a pronounced coma and an extensive tail. These features are classic hallmarks of a comet, signifying the presence of volatile materials that sublimate as the object approaches the Sun. A coma is the diffuse cloud of gas and dust that forms around a comet's nucleus as it heats up during its journey into the inner solar system. This glowing envelope of material results from the sublimation of ices, compounds such as water, carbon dioxide, ammonia, and methane, that are present within the comet's core. As the Sun's energy reaches the icy surface, the solids transition directly into gas, releasing dust particles that are carried along with the vaporized gases. The interaction between solar radiation and the released particles produces the familiar tail that stretches for millions of kilometers away from the Sun, pointing generally in the opposite direction of the Sun due to the effects of solar wind and radiation pressure. The clear presence of both a coma and tail in 3I/Atlas unequivocally demonstrates that it behaves like a typical comet, ruled by the same physical processes that govern all such objects within our own solar system. These observed features are not mere optical illusions or the result of observational errors. Astronomers take great care to verify that what they see in the telescope images reflects actual physical processes occurring in space. Multiple observations from different instruments and locations have consistently revealed the same characteristics, reinforcing the conclusion that the glowing coma and tail are genuine manifestations of volatile materials reacting to the Sun's heat. This consistency is crucial, as interstellar objects are rare and fleeting, often giving scientists only a short window in which to collect data before they recede back into the depths of space. Understanding the composition and behavior of 3I/Atlas offers valuable insight into the conditions of other star systems. Comets are considered primitive building blocks of planetary systems, preserving materials from the early stages of formation. By studying the ices and dust in 3I/Atlas, astronomers can gain clues about the types of compounds that exist in distant stellar nurseries and how they may influence the development of planets and other celestial bodies. For instance, water ice and organic molecules in comets are thought to play a key role in delivering essential ingredients for life to planets like Earth. Examining interstellar comets like 3I/Atlas expands this understanding to an entirely new level, providing a rare opportunity to compare the chemical compositions of objects from different star systems. Another distinguishing feature that separates 3I/Atlas from asteroids is its tail. Unlike comets, asteroids are composed primarily of rock and metal and do not contain significant amounts of volatile ices. As a result, asteroids passing near the Sun do not exhibit the dramatic outgassing that produces a visible tail. Even the most reflective asteroids may shine brightly, but they lack the diffuse cloud of vaporized gases and dust that characterize a comet's appearance. Observers of 3I/Atlas have noted its prominent tail extending millions of kilometers, confirming that this object is dynamically and compositionally distinct from rocky bodies in the solar system. The trajectory of 3I/Atlas further supports its identification as a comet. Interstellar comets tend to follow highly hyperbolic paths, moving quickly through the solar system and eventually escaping back into interstellar space. The rapid velocity and incoming direction of 3I/Atlas suggest that it originated from a distant star system, traveling for potentially millions of years before encountering our Sun. This long journey through the galaxy underscores the resilience of such objects, which must survive the harsh conditions of interstellar space, including cosmic radiation, collisions with micrometeoroids, and extreme temperature fluctuations. The preservation of its icy core and ability to form a visible coma indicate that 3I/Atlas has retained much of its primordial structure despite this epic voyage. Observing interstellar comets like 3I/Atlas also challenges astronomers to refine their models of how objects are ejected from star systems and the frequency with which such wanderers may visit the solar system. The discovery of 3I/Atlas, following the earlier examples of Oumuamua and Borisov, suggests that these visitors may be more common than previously thought, though they remain difficult to detect due to their small size and transient presence. Advances in survey technology, such as the use of automated wide-field telescopes and improved detection algorithms, have increased the likelihood of identifying these objects before they pass out of observational range, opening new opportunities for in-depth study. In addition to its scientific significance, 3I/Atlas captures the imagination because it represents a tangible connection to the broader galaxy. For centuries, humanity has looked to the stars and wondered whether life exists elsewhere. And while 3I/Atlas is not evidence of extraterrestrial intelligence, it serves as a reminder of the vastness of space and the potential for encounters with unknown cosmic phenomena. Its brief passage through our solar system is a fleeting opportunity to study matter that originated in a completely different stellar environment, offering insights that cannot be obtained from locally formed objects alone. As 3I/Atlas continues on its journey out of the solar system, astronomers will keep monitoring its behavior, tracking changes in brightness, tail structure, and composition as it moves farther from the Sun. These observations will provide a valuable dataset for understanding the physics of comets under varying solar conditions and for comparing interstellar comets with their native solar system counterparts. Every detail, from the rate of gas emission to the orientation of its tail, contributes to a more complete picture of how such objects evolve over time. In conclusion, while speculation about alien spacecraft often captures headlines, the mounting observational evidence paints a clear picture of 3I/Atlas as a natural comet. Its coma, tail composition, and trajectory all align with what astronomers expect from icy bodies originating from other star systems. Far from being an anomaly or a technological artifact, 3I/Atlas is a reminder of the complexity and richness of our galaxy, a cosmic traveler carrying the chemical history of distant stars into our own celestial neighborhood. By studying objects like 3I/Atlas, scientists not only satisfy human curiosity, but also deepen our understanding of the processes that shape planetary systems throughout the universe. The journey of 3I/Atlas is brief in astronomical terms, yet its passage leaves a lasting impact on our knowledge of interstellar matter and the interconnectedness of the cosmos. Through careful observation and analysis, humanity gains a rare glimpse into a world far beyond our own, a testament to the enduring power of scientific inquiry and the wonder of the universe.